and that is a very interesting point here about calculating the radius of the Earth. And this is something that is actually, inshallah, we can all understand it if you remember your high school trigonometry. The first person to attempt to do so, to attempt to calculate the radius of the Earth, was Eratosthenes, right? Eratosthenes, right? Correct? Eratosthenes? I think Eratosthenes, yes, 195 BC. 195 BC. And so that's 1,000 years before Al-Biruni. And Eratosthenes, he employed a very ingenious method which involved measuring the change in latitude of a celestial object measured at two faraway locations on the same longitude. So if you knew the exact distance between two distant locations, you would be able to calculate the radius of the Earth based upon that. Now there were a number of problems here with that calculation. Of them is that you would have to know the exact linear distance as the crow flies between two faraway locations, and that's very difficult to translate. And so Eratosthenes did in fact attempt a calculation. Al-Biruni was not satisfied with it. Al-Biruni wanted a more accurate method that did not require as many input methods, as many measurements to make, and did not require a long distance traveling. So Al-Biruni devised a more easier and a more precise method that had fewer possibilities of error. And Al-Biruni's method only involved two calculations, and it involved one location. So two calculations and one location. You didn't have to travel far and wide. And that one location required a number of things. It required a mountain, and it required a plain horizon. You couldn't have a valley or whatnot. Just a mountain followed by flat earth, or maybe even, ocean or whatnot, where you could see the horizon straight from the mountain top. That is all that is required. And so Al-Biruni, and you need only two inputs. The first is the height of the mountain, and the second is the degree of the horizon from the top of the mountaintop, right? So those are only two things that you need. And by the way, Al-Biruni calculated the height of the mountain very ingeniously, very simply as well. Not by dropping a string or something of this nature, but rather by observing the angle of the peak from two locations, P1. So he stands at P1 and he looks at the angle of the mountain. Then he goes back to P2 and then he looks at the angle of the mountain again. And he knows the distance between P1 and P2. So he knows this distance and he knows the angles from P1 and P2. And based upon that, he can calculate the height of the mountain, H. Okay, so he finds this mountain in modern day Pakistan. I kid you not, this took place in Pakistan, modern day Pakistan, in Punjab somewhere. He finds a mountain, and he then calculates the height of the mountain, H. And he does this by, as I said, a very simplistic method, simply by P1, P2, and the angles from both of these localities. By the way, there's a video that somebody has attempted to do this, and I'll put that in the links. Let's look at the link below. So let me now see if I can show you the slide that I found somewhere online. This is not from me. Okay, I hope you can see this slide here. I hope you can see this slide over here. So here's the diagram that somebody derived from Al-Biruni's writings. So remember, Al-Biruni has already calculated the height of the mountain, H, okay? And we're looking for R, the radius of the Earth, okay? Is that clear? Take a look at this diagram, understand what's going on here. Al-Biruni already knows H. He's calculated H, and now we want to calculate for R, which is the radius of the Earth. How do you do this? You go to the top of the mountain, and you are now basically standing at the top of the mountain, and you measure the angle of the horizon. You measure the angle of the horizon from the top of the mountain, which let's call it theta, okay? So theta is the angle of the horizon. You see that very clearly from the top of the mountain, okay? Now, you notice that as you're standing on the top of the mountain, you are forming a right angle triangle from the center of the Earth, okay? And one of the right angle triangles is the center of the Earth, right? The other is where you are, and the third is the horizon. The third is that horizon where your line of sight hits the horizon. Okay, with this simple, very simple high school trigonometry, you can solve for R. Why? Because cosine, as you remember, you should all remember for your basic math lessons, right? Remember, I do have a degree in mathematics, but sorry, engineering, which I have a minor in mathematics and chemistry. But yes, I did way more than trigonometry. I did partial differentials and all of this way back in the day. That I would not be able to do. I've forgotten all of that. But yeah, trigonometry, you don't forget trigonometry once you've done as much math as I had to do. But cosine, of course, remember what cosine is adjacent over hypotenuse, right? So now take a look at this triangle here, right? So you have, in our case, cosine theta. Now, by the way, theta, look at theta on the top and theta in our triangle. It's going to be exactly the same. And I hope you understand why. Because theta at the top, which is the angle that you're looking at, obviously that forms a right angle triangle. And so the angle that is remaining is 90 minus theta, which happens to be exactly what the angle of our triangle down that we're interested in is going to be. And so that is theta. And so you have now the angle that you've seen is going to be the same angle of our own right angle triangle, which is theta. So cosine theta is going to be adjacent r, the radius of the earth, over hypotenuse, which is r plus h. Okay, I hope that's clear here. So cosine theta equals r over r plus h, which is adjacent over theta. Now remember, you know h, you've already calculated h. Okay, and you've just calculated theta by standing on the mountain. So you simply solve this equation here for r. Very simple algebra, very simple trigonometry. And you get that r is h divided by secant theta minus 1. Remember, secant is 1 over cosine or inverse cosine, or to be more pedantic, secant is hypotenuse over opposite, right? So again, this is all simple stuff. You can do this yourself, calculate it out. Very simple, literally high school. Again, the ingeniousness is in its simplicity, right? And so you solve this equation here for r, and you get the equation that Al-Biruni got. And so Al-Biruni carried out this experiment, and he found out that theta was around 34 degrees. And he calculated the fact that the radius of the earth is 12,803,337 dhira, or cubits. And when you convert dhira to meters, is not quite precise in our times, but we get around 6,000 kilometers, around 6,000. The actual radius of the earth is 6,372. Okay, so Al-Biruni was 300 kilometers off. That's it, by this simple calculation. By the way, the Greek guy got 5,200 kilometers. He was over 1,000 kilometers off, and it would take many, many centuries to beat Al-Biruni's mechanism. So Al-Biruni here is calculating the radius of the earth via this very, very interesting chart here. Okay, so now let's get back to
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم